Hello, welcome to this introductory course, which will serve as a fundamental intro course to both ArcGIS and QGIS, as this is an introduction to geographical information systems. So in this course, you get the overview of what GIS is and the possibilities of GIS in your field. So in this course, I'm basically introducing what GIS is, and the guideline in my introduction to what GIS is will be to help you understand and learn the uses of geographical information systems. Will also be to help you learn how layers work. You'll also be able to differentiate between GIS features and surfaces. You also obtain preliminary understanding of feature locations, scale, and attributes. You also obtain preliminary understanding of spatial relationships between features. So this is the guideline of what you expect to understand and learn in this course. So shall we quickly jump in as I introduce to you what GIS is? So what do you think GIS is? What do you think geographical information systems is? Well, GIS is basically an integrated collection of computer software and data used to view and manage information about but about specific places where you are able to analyze the relationship between those places, and you can also model a process that will give you results with respect to those places. GIS also provides a framework for gathering and organizing location-based data and related information to that location. In particular, could be a lot of locations, so that at the end of the day, those locations could be displayed and analyzed with their specific information, which means GIS basically will allow you to study and explore everything about each and every place that you took interest to gather information about. So with GIS, you can identify and analyze the land features, climate, boundaries, population, resources, and many other things about places that interest you. In the past, you needed to use paper maps, globes, and a variety of hard copy data sources to perform these analysis. Now with a GIS, you can make maps, you can make globes, you can make data, and we have quite a number of analysis tools that are available just from any computer that has got the processing power to be able to give you that analysis, which can be as sophisticated as may be needed for you to get the results. And the beautiful thing is that once you get those results, you can map them and present them. You could also store those maps. You could share the information digitally. You can print that information. So basically, this is what GIS is. And if it's not making sense yet, don't worry, it will as we go on in this course. So here are a few examples of uses of GIS. One of the examples is you could study or create a GIS by doing a population density map, which will show you the distribution of population in relation to specific areas. And those specific areas could be provinces, districts, or townships. Another analysis you can perform with a GIS is to find locations that meet a specific criteria, you could add that to the previous example which I've given you for population distribution. Maybe you can say, I want to understand which province has got the highest number of females that are aged between 24 and 30. Quite a number of different criteria which you could make, and GIS will be able to give you those facts for you. So another example is if you are working in a real estate company, you might have an access to a GIS database of properties with associated property values that you could use to generate sales. So the properties that you are selling could be in different locations, and GIS will bring them all together in a computer and show you their locations and their associated sales data. Another example is if you work in a utility company, you might use a GIS to coordinate, map, and manage the thousands of repairs you have to complete each year. Maybe you're working for a power generating company like ZESCO, and you are receiving quite a number of complaints from different clients. It could be a water utility company. It could even be your business where you have clients in different provinces that are bringing complaints to you, and you need to maintain their, maybe you supply equipment that you install, and you want to ensure that your maintenance team responds quickly. GIS will be the solution, because you'll be able to coordinate by mapping all the complaints and also ensuring to understand whether all of them have been attended to or not. Another example is you could use GIS to analyze what is happening around a specific area. For example, if you work in an environmental agency, you might map wildlife species, habitats, and by doing so, you take up inventory of vegetation across a region to understand better the relationship between those habitats and the vegetation. As you are aware, different animals eat different kinds of food. So you can understand what giraffes like eating, what what maybe buffaloes, impalas, etc., what they like eating by mapping their habitation and also the vegetation that is there. The other examples is if you work for a water conservation agency, you might analyze areas that are adjacent to stream watersheds so that you can understand how natural features change over a period of time, how season water flow also changes, and how existing habitats also change. You can also use a GIS to map how and where things evolve over a period of time to learn about that subject movement and behavior. If you work for a public health agency, you might track an influenza outbreak geographically, or any other outbreak that might come up, and you, in so doing, you determine its origin. You'll be able to identify the distributions or clusters, which are basically the concentrations of the outbreak per geographical area, and as a result, you'll be able to identify areas of high risk. You can use a GIS also to evaluate current situations and in the process anticipate future conditions. For example, you could track and model water flooding data to provide early warning for evacuation schedules that can help save people's lives. So there are quite a number of applications and uses of GIS, which I may not be able to exhaust. Telecommunications, quite a number. But for the purpose of this class, to ensure that it is not as long, I'm sure the given examples will help you to just open up your thinking and your mind, because that's the purpose of this course, to just open up your mind to the possibilities of GIS, what you could do with it when you learn it and understand GIS. So we're now going to look at the basic principles that govern GIS. And these principles will become clearer and more understandable as you work with the software. So even as I list them down, as I explain them to you, they might not make sense. Don't worry. Don't even try to master them, but just understand as you listen, and it will make sense as you go on in the course. So one of the principles is that a GIS map contains layers. Layers is basically data or data sets that are giving a description of a feature or a surface. Layers may contain features of a surface. I mentioned about a surface. You understand what all these things are. Features have shape and size. Surfaces have numeric values rather than shapes. Features have locations. Features can be displayed at different sizes. Features are linked to information. So you've seen a lot about a feature. Feature is it's anything that's physically on the earth. It could be a house, it could be a road, it could be a building, it could be a boundaries. Those are features. So it's anything that can be presented or studied or understood. Features have spatial relationships. New features can be created from areas of overlap. Data requires management. So these are the fundamental principles of GIS. The understanding of these will make you understand what GIS is. Doesn't matter how long you've practiced GIS, but just understanding this, you can understand GIS even in a month or 2 months, and the rest will just be application of it. So GIS is not rocket science. It's just straightforward. And once these things are understood, the rest is drinking milk and enjoying all you are gaining weight or getting fat. So we look at one of the basic principles, which is a GIS map contains layers. And as you can see, there is a map there with a legend. And this map of North America shows state boundaries, lakes, rivers, terrains. It also shows the amount of electricity generation, transmission, and locations of core bases. This map is from Esri, and all the maps that I'll show here are from Esri. They're the ones who developed them. It's important to acknowledge and appreciate their efforts. They're the leaders of this profession of GIS. On this map, before we look at this map, on a paper map, you cannot separate cities from countries from the ocean, or let's say houses from a township. But in a GIS like this, you can. And as you can see, there are different layers here, which I had already mentioned when you read here. And they are color coded with this legend. So legend is basically a guide that helps you understand the features and the colors that are on the map. So you can see the color codes here, and you can relate and extract meaning from the presentation. So what we are saying is that with GIS, you can remove this if you don't need the transmission lines. You can even add more information here, but on a paper map, to be hard to do, because every time you have to print a new copy, or you have to draw. So a GIS map is made up of layers or collections of geographical objects that are alike and are defined by a visual symbol. And in this case, a visual symbol are these colors that have been color coded to help you understand. You can also see the sizes of this, which will help you understand the distribution of electricity generation. So to make a map, you can add as many layers as you want, which I've already explained to you. On this map, you can see the transmission lines that are laid on top of electricity, and you can even see the order of. So what this means is the order of presentation on the map. These are on top of this data, so you can overlay different layers on the map. And finally, layers are laid on top of the terrain and the ocean. The terrain and the ocean is the green color, this color that you're seeing here. All this is the ocean and the terrain, and everything has been laid on top. This creates an important layer or hierarchy of the map. So there's always that hierarchy, which is determined by the way you put the layers. So the second one is layers may contain features or surfaces. Still looking at the same map with the same legend, that same information. On this map, we have the core basins layer, which includes many basins, and you can see the guide here. We also have the transmission lines layer, which contains also many lines with different kilowatts. And when you see the color there, you'll be able to tell, oh, this line is this so number of kilowatts. The same is true for the states and lakes layers, which will show you the type of the state. Each layer contains many of the same type of things. So it's very important to understand that each layer will contain the same, like transmission lines in this case. It's all transmission lines. The only difference is that they have different sizes of kilowatts. And that's how layers are organized. Not all layers contain features. We will look at this in detail. For example, the ocean layer is not a collection of geographical objects, as are the other layers. It is considered a single continuous expanse that changes from one location to another according to the depth of the water. We are now bringing into an understanding of what a surface is and how it's different from a feature. So layers may contain features or surfaces. Here is a map. It's a topographic map which shows the terrain of landmass and seafloor. Like we said, not all layers contain features. Like in this case, the ocean layer is not a collection of geographical objects as are the other layers. This one is a single continuous expanse that changes from one location. That will change from one location as I move the cursor to another according to the depth of the water here. For here, it will be according to the height, because this is the water and this is land mass, which you can see. So the difference here is that as you move, the altitude of the landmass will be different. Here, the depth of the water will be different, and you can represent all those things using a surface rather than a feature. This is the power of GIS. It's also important we've looked at the differences between surfaces and feature. Now we are looking at features have shape and size. So here is a map, different map. It's an earthquake epics. It shows the earthquake epicenters and seismic hazards in Indonesia. Polygons are used to represent land masses, points to represent earthquakes, and lines to represent subduction zones. Geographic objects have an endless variety of shapes. However, they can all be represented as one of three geometrical forms: a polygon, a line, or a point. Polygons may represent objects that are large enough to have boundaries, such as countries, lakes, and tracts of land. Maybe a farm will show the extent of the farm and the area of that particular farm. The country could be a district, could be a province, could be office space. You could use a polygon to show the extent of that area. You could use lines to represent objects that are relatively too narrow to be polygons, and these are rivers, roads, pipelines, ZESCO lines, railway lines, etc., etc. You use points. Points also can be used for objects that are relatively too small to be polygons, such as cities, schools, fire hydrants. So a city, depending on the map that you want to make, you can use it as a point to show this is where the capital city of each country is, or you could use as a polygon depending on what you want to show. But it's important to understand that if you want to use a point, then you're just basically showing the locations of particular objects like city or fire hydrants. The same object may be represented by a polygon in one layer or a line or a point in a different layer, depending on the type of map that you want to make. The other thing which is very important to understand in GIS is that polygons, lines, and points collectively are called vector data. So there is what is called vector data and there is what is called raster data. So vector data is basically a coordinate-based data model that represents geographical features as points, lines, and polygons. Each point is represented as a single coordinate pair, and line and polygon features are represented as ordered list of vertices. Attributes are associated with each vector feature as opposed to a raster data model which associates attributes with grid cells. So we shall look at raster data, which is basically surfaces that we covered. The other principle to understand is that surfaces have numeric values rather than shapes. So we are looking at raster data, which I spoke about. So here is a map of raster data. A close look at this raster of ocean shows that it is composed of square cells Each cell holds a numeric value indicating ocean depth. Graphic designers will easily understand this. So here is a map, which is raster in a picture format. And then when you zoom in, what the computer sees is basically grids. As you can see on here, basically just different grids with different concentrations. And these concentrations are basically representing values. And these are the values now that we're saying that surfaces have numeric values rather than shapes. And you'll see what you can do with these values. Unlike countries or rivers, natural phenomena such as elevation, slope, temperature, rainfall, and wind speed have distinct shape. So these things don't have shape. Temperature doesn't have shape. Rainfall doesn't have shape. Wind speed doesn't have shape. So how can you represent it on a map? Instead of using vectors, which aligns polygons that will need a shape, you could use raster data to present these types of phenomena. And this is what makes GIS extremely powerful and relevant in quite a number of fields. What they have instead are measurable values for any location on the surface of the Earth. So the rainfalls could be different from one location to the other. Temperature could be different from one location. Wind speed could be different. And these are all values. And you can use these values now here and give them colors to represent the ultimate picture, which will eventually show here. And you could use these same values to have a legend here that will show that this particular area, which is more green than this area, has got high temperature than this other, or has got higher rainfall than this area, etc., etc. For instance, wherever you go, you are either at sea level or a number of meters above or below it. Geographical phenomena such as these are easier to represent as surfaces rather than as features. Like I mentioned, how can you add a feature to temperature? Because it has got no shape. Wind speed has got no particular shape. So the most common kind of surface is a raster. And basically a raster is a matrix of identical sized square cells. And each cell represents a unit of surface area, like we have seen here. For example, 10 square meters and contains a measured or estimated value for that location. And basically, a raster is a spatial data model also, which is different from vector, which we've already looked at. And this model defines a space as an array of equally sized cells, like you are seeing here, arranged in rows and columns and composed of single or multiple bands. Each cell will contain an attribute value and location coordinates. So all these will have attribute value and location coordinates, unlike a vector, which we've looked at, which stores coordinates explicitly, like you'll be able to see the coordinates. These raster coordinates are contained in the ordering of these matrices. So these same particular cells share the same value and also the same type of geographical feature. So the way the coordinate systems are stored in here, it's a little bit different from the vector. So like I mentioned, these things that I'm saying may not make sense, but don't worry. And what's important is just for you to understand for now that this is raster, it's different from vector, and everything as you begin working with the data, it will make sense. Surfaces have numeric values rather than shapes. We are still looking at this one. And in looking at this one, the other thing that we can consider is the world is not divided neatly into features and surfaces. So as you work with GIS, as you work with data, you get to be found either depending on what you're working on, if you're working on a project that is looking at rainfall, is looking at wind speed, is looking at temperature, then you most likely work with raster data rather than vector data. If you are working with population distribution, you are working with maybe you're mapping sanitation, you're mapping water facilities, you're mapping different kind of utilities, you may work with vector data. So the type of data, like we have seen, will determine what you work with. For example, polygons are often used to mark the boundaries of vegetation types, but this implies that the change from one type to another is more abrupt than it probably is, because one type of vegetation often blends into another. Vegetation can be represented not only as a polygon but also as a raster surface, with each cell value standing for a type of vegetation. So here's a very good example that shows you that vegetation can be used both as raster data or vector data, depending on what you want to understand or what you want to communicate. So this was the last part, which I wanted you to understand that depending on the project, you either work with vector or you work with raster or you work with both. Yeah. So the other principle is that features have locations. This is something that I think you can understand. Someone will say, send me a WhatsApp location. The feature is where you are. It could be at office, that's a feature. It could be at home, that is a feature. It could be at the market, or you are visiting and you want to be, those are all features. So here's an example. If you were asked to find Berlin, Germany, on a map of the world, it probably wouldn't take you very long. But suppose Berlin wasn't shown on the map. So here you'd say, Berlin is here because you can see that it has been written here, Berlin, and there is that mark. Now suppose it wasn't shown here, this wasn't there. Could you make a pencil mark exactly where it should be? Now suppose you could lay a grid or graphic over the world map, and you knew that Berlin was a certain number of marks up from and to the right of a given starting point. A graphic basically is a network of longitude and latitude lines on a map or chart, which relates to points on a map, their true locations on the Earth. So as you can see, the grid that we're talking about, which has already been laid here, it's these lines, horizontal lines and vertical lines, which are longitude and latitude. And these represent the mapped locations on the ground. So if you knew where Berlin, if you knew the coordinates of Berlin, you can use this to pinpoint and eventually come up with this location. And what's important for you to understand is that features have got locations, and those locations you have to ensure that you get the coordinate for those particular locations. In that case, it would be easy to put your pencil on the right spot, like I've already mentioned. A grid of this kind is called a coordinate system. So I'm introducing you to a coordinate system, and it is what a GIS uses to put features in their proper place on the map. On this map, a coordinate system has an x-axis and a y-axis. X-axis, y-axis. The intersection of axis is called the origin. Feature locations are specified by their distance from the origin in meters or feet, or a similar unit of measure, in this case lines of latitude and longitude. So they are measured or specified by their distance from the origin, in this case, like that and like that, then they intersect. Still on features have location. The location of a point feature on a map is defined by a pair of coordinates. Berlin has coordinates of 52 degrees and minutes and 30 minutes latitude and 13 degrees 25 minutes longitude. So east is longitude, north is latitude. So you can use these values now to pinpoint that. A straight line needs two pairs of coordinates, one at the beginning of the line and the other one at the end of that line. The line could be like this one that you are seeing here. So depending on where it's going, you need one coordinate there, another coordinate there to have a line. To have a point, you just need one coordinate. If the line bends like a river, there must be a pair of coordinates at every location where the line changes direction. That is for a line. The same holds true for a polygon, which is simply a line that returns to its starting point. So a polygon would go like that, 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 and eventually return to its starting point. That would be a polygon. So that's how points, lines, and polygons form vector data. The other principle to understand is that features can be displayed at different sizes. Here is a map. This is a utilities map at a scale of approximately 1 to 1 million, county, state, and so line boundaries are shown. On a GIS map, you can zoom in to see features at a closer range. As you do, the scale of that map changes. I'm sure you've seen Google Maps, which most people are familiar with. You can zoom in, you can zoom out. That is what we are saying, that features can be displayed at different sizes. You could see the city from the whole map of Zambia. You can see the city as an entire city, which will eventually show you where the State House is, where UTH is, where Findeco House is, etc., etc. Scale, which I'm now introducing into scale. Scale, commonly expressed as a ratio, is the relationship between the size of the features on the map and the size of the corresponding places in the world. So basically, this scale here is showing you the relationship between the size on this map with respect to its actual size in the real world on the ground. So if the scale of a map is 1 to 1 million like this one, it means that the features on this map are 1 over 1 million of, which is 1 million times smaller than their true size. So this is what the scale is all about. A utilities map at a scale of approximately 1 to 1 million county state. So what we are saying here is that whatever you are seeing on this map, because this map says 1 to 1 million, whatever you are seeing here is 1 million times smaller than their true size on the ground. That is what basically the scale is. And in GIS, you work with different scales. You work depending on the data that you are working with. If you're working at different provinces, you would see the whole map of Zambia or the whole map of Lusaka, or just a particular township, or just a particular location could be UTH. You are just viewing UTH. So those are different scales, and it will show you that that feature that you are seeing is this number of times smaller compared to the real world. Zooming in gives you a closer view of features within a smaller area of the map. Here is a map, different map from the previous one, still looking at features can be displayed at different sizes. Here is a city transit map at a scale of approximately 1 to 12,000, like building footprints, roads. So as you can see, this one now tells you that whatever you're seeing here is 12,000 smaller compared to the one on the actual ground, rather than the other one that we saw, which is 1 million times smaller. The amount of detail in the features does not change, but what details you can see is what changes. This is very important. The amount of details in the features does not change. The only thing that changes is what you are seeing. That's the purpose of zooming in. What you are seeing is what changes. A river has the same bends and the coastline has the same, so everything, it might look very small, but nothing changes. The only thing that will change is what you see, and that's what makes GIS extremely powerful. And how much detail the features have depends on the layer that you are using. Just as a paper map of the world generalizes the boundaries of Zambia or any other country more than a map of Africa will do, so do different GIS layers contain more feature detail. And all this will make a lot of sense. Do not worry. I'm sure we have internet-based maps. We have ArcGIS online platform. We've got Google Maps that a number of non-GIS professionals are acquainted with. And you will have experienced how when you zoom in, you are able to see much detail. And when you zoom out, you are not able to see certain information. It's not that that information has changed. No, it's just the presentation that changes. The other thing we're looking at is that features are linked to information. So those features that we are out talking about are linked to information. This is what makes GIS very powerful. So here is a table of country areas generalized, and you find that this information is linked to those features which we were looking at. And usually such tables in GIS are called attribute table of a layer of countries, which includes features, shape, ID, number, name, population, and area, and other things. So you could have, like we said, you want to understand a particular place, and this is what will contain all that information which you can now use to do your analysis. So a feature is more than its physical shape and location. A feature also includes everything else that might be known about that feature. For a country, this might be its population, capital, system of government, leading imports and exports, average rainfall, and mineral resources. For a road, it might be the speed limit, the number of lanes, whether it is paved or unpaved, and whether it has one-way or two-way traffic. A great deal of information exists about any feature, whether it could be humble length of sewer pipeline or vastness of an ocean or a city. Information about the features in a layer is stored in a table, like you are seeing. So information about all those layers that you have, that you can display, as many layers as you can display, will have their own attribute tables that will contain information about each and every object in that particular feature. And this is what makes GIS extremely interesting and powerful. The table has a record of each feature in the layer and a field column for each category of information that you are interested to know about that feature. These categories are called attributes, and the table is called an attribute table. So the attributes are these. These are attributes about the feature country, which will have these records, which are particular, could be states, could be provinces, etc., etc. So that's how data is basically organized. So what's important for you to understand in all this is that features are linked to information. So as you can see, still at features are linked to information. Here is an example of Brazil as highlighted. So you see, this is the table that I was showing you. So when you click in QGIS or ArcGIS, when you click and select this country, Brazil, with all that information about Brazil, you find that on the map it will be highlighted. So it will show you that this information is related to this feature here, this boundary here, which is Brazil. And this is how you get to now have insights about those features that you have on the map. Okay? Yeah. So what's important here for you to understand is this relationship. If I were to click on another object here, you find that this will no longer be highlighted, or it will be highlighted if it's still selected. And what will be highlighted if I'm just selecting one is another country, and the information will come up. So this is basically what you need to understand. So you can use this ability to locate and identify specific features. So you can have as many features as you can in a data set, and you can use this to identify where that information is. So we are quickly going to just, this is what brings GIS alive to you. So here's a map which countries belong to the continent of Asia. So I'm sure quickly in your mind, you have seen Asia there, and you know that when you look at the color codes, this is Europe, this is Africa, Australia, South America, and you can see the color code. So you can tell that all these, at a glance of just looking, are the countries that belong to Asia. Yeah. Here is another example. Which countries have a population of 1 billion or greater? And you can see China and India, just by their colors, that these are the ones that we are talking about. So we could use GIS to answer such kind of questions. Here's another example. Which cities in Asia are national capitals and which are not? So you could see the national capitals. You could see that they are represented with specific symbols. And the ones which are not national capitals, they're just cities, are not represented with these particular symbols that will show that these are national capitals. Here is another example. Which cities in Asia are capitals and have populations of 5 million or greater? So you can see. So you ask these questions in the attribute table, and when you go, or queries in the attribute table, and then you find they'll be selected, and you can see that these cities have population of 5 million and greater. So this is population distribution. Now you've got an attribute table that has population distribution. Here is another example. Similarly, you can use attributes to create thematic maps that use colors or other symbols to indicate the nature or feature attributes. So as you can see here, 1 meter resolution, 2 meter resolution, and then you have the percentages there. So this map shows the percentage of the state covered by the common land unit, the smallest unit of agricultural land that can be enrolled in a farm, administered by the US Department of Agriculture. So the other principle is that features have got relationships, spatial relationships. Here is a map which shows the utility parcels, water lines, valves for Kobe County water system in Matreleta, Georgia. So in addition to asking questions about the feature information stored in attribute tables, you can ask questions about the spatial relationships between features. For example, which features are nearest others, which cross others, which are contained by others. So you can ask these questions from the attribute table, and those answers will show here, they'll be highlighted. And you can export those features and you say these are the ones, and then you can go to them and do whatever it is that you want to do. That's what makes GIS extremely powerful. The coordinates of features are used in a GIS to compare their locations. So on the map shown, the relationships between parcel locations, water lines, and valves are established in the GIS. It is critical to the utilities distribution operation to ensure the isolation of the high pressure system from the normal pressure system, and GIS will help you to achieve this in many different situations. Still looking at this map, which provides a detail for each of the essential valves located in the high pressure water system. Which water valve belongs to which parcel? So all those questions can be answered. Which water line crosses a main road? And all those questions can be answered. Which valve affects the water pressure of which water line? By taking a closer look at the map, engineers can quickly make informed decisions on pressure problems reported in the area and determine whether extending the high pressure zone is a potential solution or not. So the other relationship is new features can be created from layers of overlap. Regionally significant landscape features are derived from other features in the area surrounding Portland, Oregon. Queries about attributes and spatial relationships identify existing features based on whether they have or do not have certain qualities. To solve some geographical problems, however, it is necessary to use a GIS to create features from existing ones. On the map shown, a GIS database containing layers such as soils, slopes, rivers and streams, wetlands, flood plains, POCs, and natural areas, significant habitat inventory, greenways, and natural hazard data was used to identify regionally significant areas. So depending on the data set that you have and the expertise that you have, so you can use certain information, you can use the certain type of data sets to derive new information from that data set, which you can now use to make decisions or make certain changes. And this is what this means, that new features can be created from areas of overlap. So the other principle, which is the last one, is that data requires management. Quite important to understand, because GIS data can quickly grow complicated and you don't know which is what, where is what, and everything. So early in the planning stages of a GIS project, you must decide how to organize your spatial data so that you are not confused. For example, you could say by type, by location, by granularity, so on and so forth. Regardless of which approach you use, recording metadata. Metadata is basically information about your data, the information that you used to collect the data that you have for your spatial data is key to your data management strategy. Where to store your data is usually a problem. Do you want to store it on a local machine? What if it crashes? Do you need to store it in a web server online? etc., etc. Those are things that you need to understand before you embark on an assignment or a project. Small projects can be stored on a local drive. Some datasets are extremely large and need to be accessed by many people. In this case, storing data on a central server would be a good situation so that people can just have login details and access. For example, large-scale shared data strategies such as those that are employed by government agencies, local governments, private companies, individuals who collect large data sets. Mostly these will use GIS servers or cloud networks to ensure that their data is very secure, and they'll reduce redundancy where someone will give an excuse to say, I'm waiting for this one to give me the data, I can't access it. There will also be compatibility with a wide range of systems. So having gone through all these fundamental basics, I think now you have some idea of what GIS is and what it can do. And from now, this is a class that you can come back, you can pause, come back as you do your courses, your lectures, as you do them, you can come back to just refresh your knowledge. So it has been an interesting journey with you, and I'm sure that by now you have some idea of what GIS is, and your mind has been opened up to the possibilities of what you will do in your profession or in your career or in your job or in your business with this kind of information that you are getting. So this is relevant whether you are going with QGIS or you're going with ArcGIS. These are the fundamental principles that those softwares have been built on. So see you in the next class. Bye-bye.